myself Dr. Anuj Purwar. Today we will discuss design of coagulation and flocculation part 2. Jar test. It is very difficult to calculate the optimal dose of the required coagulant without carrying out a laboratory test which is known as jar test. The coagulant mostly used is alum. The process proceeds in two stages. First stage is marked by the neutralization of electric changes. In the second stage, flocculation is brought about by slow stirring. After adding alum in raw water, aluminium ions are obtained. Color turbidity particles in raw water are negatively charged. The flock forms again have the property of arresting the suspended impurities in water during its downward travel. Thus, microflocks have property of adsorption, which removes colloidal particles of clay and other fine particles. The minimum dose of alum which produces maximum residual turbidity is called optimum alum dose. This optimum alum dose is determined in order to estimate beforehand and quantity of alum required for water treatment plant with maximum economy. 1 liter of raw water is taken in 6 beakers and they are placed side by side as shown in figure. This is a jar apparatus. Different amounts 1.5, 2, 2.5, 3 and 3.5 milliliter of alum solution is added to all the 6 beakers respectively. The content of beakers are stirred rapidly for 2 to 3 minutes during the first stage of coagulation at the rate of 100 to 120 rpm. Then the contents are stirred at 20 rpm for 20 minutes. The liquid is finally allowed to settle down. The solution of each beaker is checked for turbidity. The smallest dose of alum that produces good flock and less turbidity is taken as optimum dose for the particular sample. Here the observation for the jar test. For all 6 jars, here the amount of coagulant quantity is shown. Let best flock was found in jar number 5. Strength of alum solution is equal to 10 milligram per milliliter. Dose of coagulant then 30 milligram. So the recommended dose of the coagulant is the 30 milligram per liter. Here the example, a dose of 60 milligram per liter of alum is used in coagulating a turbid raw water. So calculate the natural alkalinity consumed, what are the changes in the ionic character of the water, and what concentration of aluminium hydroxide is produced. So the equation for the reaction is the Al2SO3 18H2O plus 3CaSCO3 whole twice is equal to 2AlOH whole thrice plus 3CSO4 plus 6CO2 plus 18H2O. So from the our equation 666.7 gram commercial alum reacts with the 300 gram alkalinity as CaSO3. So 1 milligram per liter alum will require, then alkalinity is equal to 0.45 milligram per liter. 60 milligram per liter will require, so answer comes the 27 milligram per liter as CaSO3. Now 60 milligram per liter of alum is equivalent to 0.6 m equivalent per liter. So 0.6 m equivalent per liter of sulfate is added to the water as CSO4. The aluminium ions precipitate out of solution. The calcium content is unaffected and 0.60 m equivalent per liter of bicarbonate is converted to the carbon dioxide. Part C. From the equation above, 666.7 grams of commercial alum reacts to produce 156 grams of the aluminium hydroxide. So AlOH voltage produced is equal to then 14.04 milligram per liter. Another example, a surface water flows of 25,000 millimeter cube per day is coagulated by adding 50 milligram per liter of ferrous sulfate and an equivalent dose of the lime. How much lime is required at a purity of 85% calcium oxide. So here ferrous sulfate consumption is equal to 50 into 25,000 divided by the 1000. Then answer comes at 1250 kg per day. An equivalent of FeSO4 would react with an equivalent of 85% CaO, which is the 32.941. So lime dose is equal to 1000 into 32.941 divided by 139 is equal to 236.98 kg per day. Clarification: the chemically assisted sedimentation, comprising of several separate processes of treatment which make up the complete system, is known as the clarification. This system is designed to clear a water as much as is desired or possible of suspended material before it goes to filter. It is a complex phenomenon having following three stages: adding of measured quantities of chemicals to water and their mixing, formation of precipitate which coalesce or coagulates and forms floc, and sedimentation. Now, chemical mixing. The main objective of chemical mixing as applied to water treatment is to obtain uniform dispersion of the chemical in the main flow of water so as to avoid local over or underdosing, which in turn prevent the chemical reaction process going to completion. For example, an adequate mixing of aluminum sulfate can impair the formation of a good floc in the clarifier and would result in poor plant performance or wastage of chemical or both. The addition and mixing of chemicals to the main flow of water is a continuous process and is frequently described as rapid or flash mixing. Chemical concentration. In chemical treatment, solutions which are used are usually dilute. In effect, 5 to 10 part of the reacting chemicals is being added to 90 to 95 part of the water to obtain 100 part of the solution. Most of the reactions are exothermic and call for the appropriate sequence of addition of the chemical to the water in order to prevent chemical accident. Now, design details. The design of a mechanical type clariflocculator using rotating blades, a knowledge of basin dimension, blade dimension, and speed is necessary. It is also necessary to compute the power and determining the values of velocity gradient g and the dimensionless expression g. Following is the guideline for the design. The power required is 0.5 to 15 watts per meter cube of flow per hour. The peripheral velocity of pedals should be in range of 0.15 to 0.6 meter per second. The energy consumption is 0.75 to 2 kilowatt hour per milliliter of water treated. Flocculation period 20 to 30 minutes. Loss of head 15 centimeter. The total pedal area should be 20 to 50% of the tank sectional area in the plane of the shaft. Horizontal velocity of the flow 0.75 meter to 1.5 meter per minute. Distance from shaft to shaft is 2 to 4 meter. Depth of tank 2.5 to 4 meter. Drag coefficient CD is equal to 1.8 for flat plates. K is equal to 0.25. Nu is equal to 1 to 5 rpm or more. The usual retention period is 10 to 30 minutes. Velocity gradient g is equal to 20 to 75 per second. Gt is equal to 2 into 10 to the power 4 to 6 into 10 to the power 4 for aluminium coagulant. N is equal to 1 into 10 to the power 5 to 1.5 into 10 to the power 5 for the ferric coagulant. Combined coagulation cum sedimentation tank. Putting the mechanical part in the system makes the system cumbersome and expensive also. Flocculation tank is sometimes combined with sedimentation tank to make the system economical. The floc chamber without any mechanical device is combined with sedimentation chamber. The depth of the floc chamber is kept around half that of settling chamber. The detention period for the floc chamber is kept around 50 to 30 minutes, whereas for settling tank it is around 2 to 4 hours. The water from mixing basin enters the tank and the clarified water comes out of the outlet end. Depth of the sedimentation tank varies from 3 to 6 meter and cleaning is done at an interval of the around 6 months. Here in picture coagulation plus sedimentation tank is shown. Example on the designing of this coagulation and cum sedimentation tank. Design a coagulation cum sedimentation tank with continuous flow for a population of 51,000 with a daily per capita consumption of 135 liters. So first design the settling tank and then the flock chamber. So set for the settling tank, average daily consumption is 50,000 into 135 is equal to 6.75 into 10 power 6 liter. Maximum daily demand is equal to 1.8 into 6.75 into 10 power 6 liter is equal to 12.15 into 10 power 6 liter. Assume detention period as 4 hours. So quantity of water to be treated during the detention period is equal to 12.15 into 10 power 6 divided by 24 into 4 is equal to 2.025 into 10 power 3 meter cube. Assume an overflow rate of the 1000 liters per hour per meter square and QBL is equal to 1000. Then Q is equal to 12.15 into 10 power 6 divided by the 24 is equal to 506.25 into 10 power 3 liter per hour. So plane area or is equal to B into L is equal to 506.25 into 10 power 3 divided by the 1000 is equal to 506.25 meter square. Keeping length of the tank 3 times that of the width. So B is equal to root 506.25 divided by the 3 is equal to 12.99 approximately is equal to the 30 meter. So length is equal to 30 into 3 is equal to 39 meter. Hence tank size may be taken as 39 into 30 into 4 meter. Provide 0.5 meter extra depth for sludge and 0.5 for freeboard. Then size of the tank is equal to 39 meter into 30 meter into 5 meter. Now design of the flux chamber. The length of the flux chamber which will be provided at entry will be extra in addition to 39 meter length of the settling tank. Assume effective depth in the flux chamber as half the depth in the tank near the flux chamber. So depth of the flux chamber is equal to 4.5 divided by 2 is equal to 2.25 meter. Assume detention period as 15 minutes. So capacity of the chamber is equal to 12.15 into 10 power 3 divided by 24 into 15 divided by 60 is equal to 126.6 meter cube. Plane area is equal to 126.6 divided by 2.25 is equal to 56.3 meter square. Using same width of the 13 meter, then length of the flocculation chamber is equal to 56.3 divided by 13 is equal to 4.33 meter. This is equal to the we can take the 4.5 meter. Another example. Design a circular flocculator for treating water required for a population of 65,000 with a daily per capita consumption of 135 liter. Assume surface loading rate at 1000 liters per hour per meter square. Now, average daily consumption 65,000 into 135. Maximum daily demand is equal to 1.8 into 65,000 into 135. Then is equal to 15.795 into 10 power 6 liter. Now the design of surface area of the tank 15.795 into 10 power 6 divide 24 into 1000 is equal to 658.125 meter square. Now take the two tanks. So area of the each tank is equal to 658.125 divided by 2 is equal to 3 to 29.06 or approximately 330 meter square. Assume detention period is equal to 3 hours. Then volume of the tank is equal to 15.796 into 10 power 6 into 3 divided by 24 into 1000 is equal to 1974.5 meter cube. So water depth in tank is equal to volume divided by the area is equal to 1974.5 divided 660 is equal to 2.99 or approximately 3 meter. Provide zero point 0.5 meter for sludge and zero point 0.5 meter as a freeboard. Then total depth of the tank is equal to 3 plus zero point 0.5 plus zero point 0.5 is equal to 4 meter. Flocculator surface area is equal to pi by 4 into in bracket d square minus d1 square. This is equal to the 330. So d value of d is equal to 469.2. d1 is the diameter of the flocculator, 7 meter. So and d is equal to, here the value is equal to the 21.6 or approximately 22 meter. Design of flocculator. Assume detention period for floc formation is equal to 20 minutes. Volume of flocculation chamber is equal to 15.795 into 10 power 6 into 20 divided by 1000 into 60 into 24 is equal to 219.4 meter cube. Assume depth of flocculation zone is equal to 3 meter. So area of flocculation zone is equal to 219.4 divided by 3 is equal to 73.133 meter square. Provide two tank. So area of each tank is equal to 73.133 in divided by 2 is equal to 36.56 meter square. So diameter of the flocculator d1 is equal to 6.82 meter or approximately 7 meter. So this is all about the sedimentation process with the flocculation. Thank you.